Hi, this is Mark Berkey with Berkey Academy, and today I'm going to respond to a question asked by one of my YouTube channel viewers. And I made a video recently where I showed how to solve an equation like this, where x is an exponent, say 5 to the x equals 10, using logarithms. And let me show you that and my website very quickly because I'm going to upload the worksheet and the graphs that we're going to use here to my website so you can download these to follow along. I recommend you go download and print this out now so that you can have it in front of you. Let me show you where that's going to be. So if you go to my website, www.berkeyacademy.com. This is where I index all my videos. For my math related videos, I don't have a special section yet. I do have for my stats, econometrics, micro, GIS, spatial stats, and computer stuff. But for my math stuff, right now, it's just right here under random mathematical musings. So this is where the link for this video will go. But also I'm going to put the little worksheet with the graphs so you can do it yourself along with the video here under Files. So click here, Files on the left side. And here you can download files that go with my videos. And I'll call this file Newton1.pdf so you can print this out and see what's going on. So anyway, so this is kind of what we're going to work with down here. Basically, here's the question they were asking. You showed us how to solve 5 to the x equals 10, but what about x to the x equals 10? Or even x to the x to the x equals 10? Is there some way to solve for a number like that? And the way he phrased it is he asked, is there an exact way to solve this? And the answer is sort of no and sort of yes. Now, when you say exact answer, what we mean in math is an analytical solution. That's what we mean by an exact answer. And in many cases, there is no exact answer. We have to approximate it. And what's more, most answers you get from your calculator are going to be approximations, especially anytime you hit the sine key or the cosine key or the square root key or the e to the x key or logarithms. Most of those kinds of answers you get from a calculator are going to be approximations, very good approximations, but nonetheless approximations. And so don't worry about the idea about whether something's an exact answer or not. What you want is a method or an algorithm to get as accurate an answer as you need. So you can get an answer that's an approximation, but it might be accurate to 100 decimal places. Well, that's plenty for most cases. So what I'm going to do is show you a method. It's called Newton's method. It was invented by Sir Isaac Newton, and of course he lived in the late 1600s and early 1700s. I'm going to show you how to use Newton's method, but what's even more important, and this is why I'm doing this video, is I'm going to show you why Newton's method works using a graphical interpretation. It's fun. It's going to be fun. And I've never done this. I kind of know why it works, but I've never actually sat down and gone through and graphed the answers. So that's why I'm taking the time to do this. Now, first I want to go through an example where I solve a simple equation we understand, and we have a button on the calculator to solve. And then we're going to tackle this x to the x equals 10 problem and see how we can come up with as accurate an answer as we want for any function. It's not just this kind of function, but it's any function really on the planet. As long as you can calculate the answer, say x to the x, as long as you know how to do that, you can solve for what value of x should go in this equation, even if there's no button on the calculator that does it readily for us. So let's get started here. So Newton's method, again, I'll put this sheet on www.berkeyacademy.com. I'll call it Newton1.pdf. Go print it out. I recommend highly doing that. So here, what we're going to learn is how to approximate solutions to any function using Newton's method. Some people call this Newton-Raphson method, the Newton-Raphson method, because another guy named Raphson, of course, did some work on improving it. It's what we call a numerical method. A numerical method is just a way to approximate numerical answers and try to find a quick way that's also very accurate. And we're going to do a graphical interpretation, so that's going to be the fun part. So I'm going to go through the method and how it works very quickly. There are other videos showing you how it works. I'm going to show you why it works. That's much more important to me. So here's the method. It says, for any function f of x, let's start by using x squared as our f of x. F of x equals y, so f of x is x squared, y is 10. The method says make an initial guess for the answer. And so as an initial guess, I would choose 3 as my initial guess because I know 3 squared equals 9, and so that's a good initial guess. The second step says find f of x0, which just says plug your initial guess into your function. So 3 squared equals 9. That's what I've done right here. F of x0 equals 9. Now, the next step is where it gets interesting. Make a second guess that's better than the first guess. So how do we do that? And it doesn't necessarily have to be a better guess, but it works better if it's a slightly better guess. So how could we make a better guess? Well, let's cheat here so that this works well. When we do the x to the x one, we won't cheat. We won't have any idea what's going on. But let's cheat here. On our calculator, we have a button. If we want to solve x squared equals 10, all we do is take the square root of 10, and that gives us x. So the answer we're really looking for here is 3.16227766, but this is an approximation given to us by the calculator. What Newton's method allows you to do is approximate this answer better, right? You could carry this out to 1,000 decimal places using Newton's method if you wanted to go through Newton's method 10 or 12 times, right? So you have to keep getting better and better. So let's make a better guess. Let's make our better guess here. Let's see. Here, I'll just edit this little line right here. And we call our better guess x1. So make a second, which is a better guess, x1. You want to make x1 kind of close to the original guess of 3, but hopefully a little bit better. So let's just choose something a little bit bigger than 3, because we know, since 3 squared is 9, that the right answer has to be a little bigger than 3. And so let me just choose something a little bigger than 3, 3.1. Now, you don't have to guess 3.1. You could guess 3.05 or 3.2, and this method would still work very well. But let's just go with 3.1. And then, once you make that slightly better guess, see if it's actually a better guess. So plug it in and find f of x1. So what is 3.1 squared? Well, let's put that in our calculator. 3.1 squared equals 9.61. So f of x2 equals 9.61. So that is a better guess. We're getting a little closer to 10 when we square it. Now, the next step is kind of the one that's weird, that if you don't look at a graphical interpretation, you're not going to understand what's going on here. Let's just do it, and then we'll look at why this makes sense. Calculate some number r, and r equals f of x1 minus f of x0. Well, what in the world is that telling us to do? Well, what it's doing is telling us to take the difference between the answer of the better guess. Oh, I'm sorry. That's not f of x2. That's 1. Please forgive me. x1 is 3.1. 3.1 squared is 9.61. So we take the 9.61, we subtract the first kind of guess answer here, which is 9. So 9.61 minus 9 is 0.61. So that goes over here. Let's see. 0.61. And then what we're going to do is we're going to divide that by x1 minus x0. So x1 is just 3.1, our slightly better guess, minus our initial guess, 3. So 3.1 minus 3 is 0.1. So 0.1. And that's equal to this number r here that we're calculating. And so what we're finding is that that equals r, and that equals 6.1. Good enough. Here's our last step in Newton's method for one iteration. We could go through and do this again and again to get even better and better answers. The last step says to get x2, which will be an even closer answer to the solution, x squared equals 10. So our even closer answer, x2, is take the number x1, which is our slightly better answer, 3.1, and let's adjust it. Well, how do we adjust it? Well, we add something to it, and we add y minus f of x1 divided by r. Well, let's do that, and let's see what we actually get when we do such a thing. So x2 equals 3.1, that's our slightly better guess, plus, what's this adjustment? Y, well, that's 10, minus f of x1, our slightly better approximate answer, 9.61. And then we want to divide that by r, 6.1. 6.1. And that's the part that always bothers me. What is that 6.1 and where does it come from? Well, let's see what we get when we actually do this answer. Do it on your calculator along with me and see what you get. Well, 10 minus 6.1, so this is 3.1 plus 10 minus 9.61 is 0.39. And then we're going to divide that by 6.1. And so what we're going to get is our better approximate answer is 0.39 divided by 6.1 equals 0.0639. So 3.1 plus 0.0639, 34426. I'll just carry that out to all the decimal places on my calculator here. Equals, and 3.163934426. Now let's compare that to the answer that the calculator gave us over here when we just did the square root of 10, and my, look how close that is. That is an extremely accurate answer. Now suppose that wasn't accurate enough for us. Then all we would have to do is do this same process over again. And to do the same process over again, here's how we could do this. Use, kind of go back one step in the process and do it again. Let's just do that real quickly to make sure that we understand how that happens, because I remember the first time somebody showed me this, they just said, yeah, and you can do it again, but they didn't really show how. So let me not be guilty of that same sin. If you want to do it again, then make this better guess here, the 3.163934426. So here's what I'm saying. Use x2 everywhere you see x1. Use this x1 everywhere you see the x0, and what we're going to do is we're going to calculate a new x2. We could call it x3. But let's go ahead and do it, so I'm not just talking here. We're going to calculate a new r. So here's a new r. Let's call it r2 in this case. r2. So r2 is going to be equal to f of x1. Well, now f of x1, we're actually using this number for x1, right? We're going to use that f of x1. So we want to figure that out. Well, let's figure out what that is. F of x2 actually. Square this. Let's see how close we get to 10. And what we get there when we square it equals 10.0104810.5. Now I'm going to use a ridiculous number of decimal places here because our goal is to get this to be very, very accurate. So what we're doing is we're pretending that now this best guess is like our better guess from before. We're going to treat that like it's x1. So let's just type this here so we kind of remember what's going on. We're going to treat that like it was x1. We're going to treat that like we used to f of x1, right? And we're going to use our old x1 as this x0, right? So we're just using our better, improved last step to go through an iteration again. And so we're going to treat x0 like our 3.1, our better estimate, and we're going to treat f of x0 like 9.61. I hope I'm not being too confusing here. Let's go through and do this again and see how much better we can get. So let me actually highlight this. This is the true answer right here. This is the real, well, when I say real answer, it's what the calculator gives us. It's not perfect, but it's going to be pretty good. We're going to get something almost exactly equal to that in this case. So let's go through. We calculate a new r. So new r, r2 here equals f of x1 minus f of x0. Well, now we're going to use 10.0104 8105 minus 9.61. So minus 9.61 equals, all right, so we get 0.00481052. So that's the top there, and then we're going to divide that by the bottom, which is the difference between these two guesses. Our really good guess here, which is 3.163934426, minus our not so good previous guess, 3.1. So 3.163934426 minus 3.1 equals, okay, so we're going to divide that by the 0.063934426. So our new R2 equals 6.263934, so 6.26393426. And again, I'm going to use all these decimal places because the point here is for accuracy. 6.26393426. And that's our new R2. Okay, so or our new R here. And now we're going to do this one last step right here. We're going to plug everything in here. We're going to take our last best guess, which was our 3.163934426, and we're going to adjust to that. We're going to add to it y minus f of x1, which is this, squared, which is the 10.0148105, divided by this r. And so let's go through and do this one last step here. And let's call it R3 because, well, sorry, X3, because this is our new and even more improved guess. 3.163934426. But now we have to adjust it, and our adjustment is, how far off is this 10.010481005? So 10 minus that. And so 10 minus this is going to be negative 0.01. We can do this in our head because it's just the difference here. So 10 minus this is negative 0.010481005 divided by that new r, 6.26, yada, 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 39344426. Okay, so pause the video, calculate it yourself, and see what our new improved estimate is. And our amazing better estimate is x3 equals 3.162261188. Now, let's see how close that is. Let's line this answer up with what the calculator gave us here. And you see how very, very extremely close this is getting. 3.1622, and instead of a 7, we have a 6. So we are getting the same answer down to almost 5 decimal places as the calculator. And if we wanted to do this one more time, we would probably get almost exactly what the calculator gets here. Now, we know it's working, but why does it work? And this is what is the most important thing. We've spent a lot of time talking about how to do it, but why does it work? Let's go down here and look at a graph and try to understand why it's working. So here's a graph of y equals x squared right here. And what we're going to do is we're going to zoom into this little region right over here where the action is taking place. And we're going to go through our first round of answers. So remember, our first round was, our initial guess was 3. 3 squared is 9. We made a little bit better guess, 3.1. And that squared is 9.61. And then we plugged that into this formula to calculate an R, and R was 0.61 over 0.1 equals 6.1. And then when we plugged that into this formula, it gave us our better estimate, which was the 3.1639344426. Okay, so let's see what's going on and how that actually works. So we're going to move over here and zoom in to where the action is. And I've labeled here what's going on here. Let me move some of these numbers out of the way so they don't clutter up our graph. Okay, so this line right here is for y equals 10. This is y equals 9 right along here. And this is the function y equals x squared, the red line that we're trying to get to. Let me plot a couple of important points here. Here's our initial guess. All right, and I'm going to make that a little bit smaller so we can really focus on exactly what's going on here. And let me make our initial guess blue. Well, blue. Yeah, we'll make our initial guess blue here. And then our second guess, we'll call that green. We'll make that green. So let me... And our second guess was 3.1 might be a better answer to the square root of 10. And when we square 3.1, we get this answer 9.61. So it's going to be right around in here. Let me get that. Okay, that's pretty good right there. And let me color that green. And then the answer we really want to know, let me make that in red, is right here. Now we don't know exactly what that is. I'll make it red. But we know that we're looking at 10 on the y-axis. And then what is it on the x-axis we're looking for? Well, something a little bit bigger than 3.1 is all we can tell from the graph. So what is Newton's method doing? Let's look at the steps that it had us go through. So what it asked us to do was to calculate this number r. So let me move some of this stuff down here so we can see it. And it said r is, take the difference between f of x1 minus f of x0. Well, what is that doing? Let's see. Well, it's saying to look at the initial guess squared, which is 9, and look at the difference between that and the better guess squared, which is 9.61. So let me draw a little line there. It's asking, what's that distance between 9 and 9.61? And so that difference there is 0.61. Let me type that here and resize it so that we can see where it goes. What's that distance right there is 0.61. I'll make it skinny. And to calculate this number r, let's go back up to the formula here. R is equal to the distance between f of x1 and f of x0, which is 10 minus 9.61. 9.61 minus 9. Divide that by the difference between our initial guesses, the 3.1 and the 3. And so, okay, let's zoom into our picture here again. what's the difference between 3.1 and 3? Okay, so let's draw a little line there. And I'll give this a different color here. Well, that difference is 0.1, obviously. So let me label that up there. 0.1. And let me make that kind of wide and short. So we see that distance right there is 0.1. Now, r is just the ratio of those two things. 0.61 divided by 0.1 equals 6.1. So that's what we got for r. R equals 0.61 divided by 0.1 equals 6.1. Now, what are we doing when we calculated that number r? Let me make that a little smaller there. What we're doing is we're calculating the slope of this line between here and here. Let me make that yellow and transparent so we can see through it there a little bit. So 0.61 is the rise, 0.1 is the run, and so the slope of this yellow line segment is just the slope between the initial guess and the better guess. What's the slope of the 2 points, between the 2 points of our initial guess and our better guess? And this is what Newton realized would help us make an even better guess. And let's see how that works. So rise over run, 0.61 over 0.1 equals 6.1. So the 6.1 is just that slope. So let me draw a little box around that r that's yellow so we can see that that's the slope of that little yellow line segment. So how do we use that information to come up with an even better guess? Well, here's what we do. The last step of the problem. So I've copied and pasted this function for our even better guess so that we can see it right here. So the even better guess says take the information we used from the progress we made between our initial guess and our slightly better guess. And what we want to do here to get our, sorry, a pop-up window there happened for some random reason. Take our slightly better guess, the 3.1. So let me type that in here. Take the 3.1 and update it somehow. So what do we update it with? Well, we're going to adjust it by taking y minus f of x1 divided by r. So y is 10 minus f of x1, that was 9.61, I believe. Yeah, 9.61, that's right. And then take that distance and divide it by this mysterious number r, that's just 6.1. Well, now that 6.1 isn't so mysterious because we know that 6.1 is just the slope of this little yellow line segment here. But how in the world does that get us a better estimate here? Well, let me show you exactly what this formula is doing. 10 minus 9.61 is calculating this distance. Let me zoom in again. Let me resize this. When I zoom in, it'll get super large. So what we're looking at here is the distance between here and here. That's a known quantity. 10 minus 9.69. Let me adjust some of these other things out of our way. So 10 minus 9.61 is 0.39. So let me label that. So there's the 0.39. I made this little line segment blue, and then the 0.39 is the insides are blue. So that height is 0.39. And so what we're trying to do here with this adjustment is trying to calculate how much should I add to the 0.31. All right, so we have the 3.1. How much should we add to the 3.1 to get an even better estimate of what x should be? We know it's something bigger than 3.1, but how much bigger? So how much should we add to the 0.39 to get a better estimate? And so that's where this part comes in. We take the height, which we know. We take the slope, which we don't really know, but we do have an estimate. So here we're using a little bit of trigonometry here, basically. What we're doing is we're assuming that this line segment that's orange, let me reduce the opaqueness there. What we're doing is assuming that this orange line segment has the same slope as the yellow line segment. Now they don't, because this is actually a curve. When we zoom out, we see that this y equals x squared function is curved, so the slopes aren't going to be the same between those two little regions, but when you're in so close, they might as well be, right? They're going to be very, very close to being the same slope there. So we're assuming using that same slope, if we know the height, then certainly we can find this other side of the triangle. And now there are a few different ways we could do it. Let me draw a little line segment there, and we'll make that some kind of pink. And so what we're doing is we say, well, if we know the slope here is approximately 6.1 and the height is 0.39, then let's solve this equation to figure out how much further over we would go to get closer to this red point, which is kind of our target. And so how does this function actually do this here? Well, let me demonstrate this for you. We know that r is approximately 6.1, so that's the rise over the run. Right? So if 6.1 equals the rise over the run, and we know the rise is 0.39 over the run, then all this equation here is doing is solving this for run. So the run must be equal to the rise, or 0.39, divided by 6.1. And that's what this is doing, 0.39 divided by 6.1, and that gives us this little pink part right here. And as we found before, when you take 0.39 and you divide it by 6.1, you get 0.0639 34426 is the distance of that little pink there. So let me highlight that in pink so that we can see that that's exactly what we're talking about. And so to recap one last time, if we start right here at 3.1, our green point, and I guess I should make that a little bit smaller. If we start at this point, which is at 3.1 and 9.61, and we want a better estimate, go up 0.39, add 0.0639 to our estimate of 3.1, and that will give us our even better estimate of 3.1639 and voila. And again, if you ever want to repeat this to get even more and more and more accurate, all you have to do is do this same formula again, which we did. Newton's method, run through it again, but on our graph, we would be zooming in so far here to do our little lines that it's not really practical to graph that anymore. But this is really the kind of graphing where a free program like Inkscape that I'm using here, which is called a scalable vector graphics format, it really comes in handy because as I keep zooming in and zooming in and zooming in to these lines that I've drawn within the program, everything's still smooth and still really clear and easy to see. So let's actually plot that one last point as accurately as we can, our new estimate, to see how close we are to our red dot real quickly. Okay, if you really, it's probably more going to be more accurate than even my drawing here, because this grid isn't going to be really perfectly accurate, but we know that this gray line right here is 10, and that right here each of these little blocks are 0.2. So this is 0.2, 0.4, 0.6, 0.63, and 10. I mean, it's just so close on to where that where the exact answer is that it's just impossible even to see the difference zooming into this graph. And again, why is that? Well, because our approximation here, even after one round, was just so close to what a calculator gives us, and after 2 rounds, practically no difference for most kinds of calculations. Well, this video's gotten kind of long, and I'm out of time for today, so what I'm going to have to do is come back later on, and I'll make that a second video where I show how we can use Newton's method to solve this kind of equation, x to the x equals 10, and we'll graph it as well. And I'm going to use the same handout. So down here, just to give you an intro, I thought this was interesting. When I plot x to the x between 0 and 1, it actually dips down and then goes back up. Right here, x is 1 and y is 1. Because 1 to the 1 equals 1. 1 to the first power equals 1. So with values less than 1, x to the x dips down and dips back up. If you look at a graph of x to the x from 0 to 3, you see that dipping down and coming back up. But from that point forward, x to the x is going to get steeper and steeper and steeper and higher and higher and higher. And so if we want to solve, what we're going to do in the next video is try to figure out, now graphically we can see that this function, x to the x equals 10, is going to be somewhere around this point. So x is going to be graphically somewhere around 2.5. But we're going to use Newton's method to come up with a very precise answer to what is x when x to the x equals 10 in the next video. I hope you'll join us.